Welcome to the Science of Emotions podcast with Ruben Singh, MD. In today's episode, we're going to discuss the theory of constructed emotions. Uh, this theory was proposed by Lisa Feldman Barrett. We will be discussing her 2017 article, The Theory of Constructed Emotions, an active inference account of interoception and categorization. Now, theory of constructed emotions is in contrast to the theory of basic emotions that we discussed in a previous episode, especially Jack Panksepp's theory. So, Lisa Feldman Barrett proposes this theory as a contrast to the theory of basic emotions. Ancient philosophers and physicians believed in a human mind to be a collection of mental faculties. They divided the mind not with the understanding of biology or the brain, but to capture the essence of human nature according to their concerns about the truth, beauty, and ethics. The faculties in question have morphed over millennia, but generally speaking, they encompass mental categories for thinking, that is, cognitions, feeling, emotions, and volition. These mental categories symbolize a cherished narrative about human nature in Western civilization. That emotions, that is, our inner beast, and cognition, evolution's crowning achievement, battle or cooperate to control behavior. Affective neuroscience takes its inspiration from this faculty based approach. Scientists begin with emotion concepts that are most recognizably English, such as anger, sadness, fear, disgust, and search for their elusive biological essences, that is, their neural signatures or fingerprints, usually in subcortical regions. Here, Barrett seems to be referring to Jack Panksepp's subcortical basic emotions pathways. This inductive approach assumes that emotion categories we experience and perceive must be as distinct in nature. If the history of science has taught us anything, however, it is that human experience rarely reveals the way the nature and the natural world works. Physical concepts are free creation of the human mind and are not, however, it may seem, uniquely determined by external world. The last 2 decades of neuroscience research have brought us to the brink of a paradigm shift in understanding the workings of the brain, setting the stage to revolutionize our study of emotions. So, in this article, we turn the typical inductive approach on its head. We begin not by mental categories, but with the structure and function of the brain, and from there, deduce what the biological basis of emotion might be. The answer, author suggests, will look something like the theory of constructed emotions. This theory was formerly known as conceptual act theory of emotions. To begin this discussion, author first outlines enough background of brain structure and function to start asking informed questions about the biological basis of emotions. What is a brain? A brain is a network of billions of communicating neurons bathed in chemicals called neurotransmitters, which permit neurons to pass information to one another. The firing of a single neuron or a small population of neurons represents the presence or absence of some feature at a moment in time. However, a given neuron or a group of neurons represent different features from moment to moment because many neurons synapse onto one, that is, many to one connectivity. And a neuron's receptive field depends on the information it receives. That is, it depends on its neural context in the moment. Conversely, one neuron also synapses on many other neurons, one to many connectivity, to help implement instances of different psychological categories. As a consequence, neurons are multipurpose. When the brain is viewed as a massive network rather than single organ or a collection of mental modules, it becomes apparent that this one anatomic structure of neuron can create an astounding number of spatiotemporal patterns, making the brain a network of high complexity. Natural selection prefers high complexity systems as they can reconfigure themselves into a multitude of different states. Brain achieves complexity through degeneracy. The capacity for dissimilar representations, that is, different sets of neurons, to give rise to instances of same category, for example, anger, in the same context, that is, many to one mapping of the structure to function. Degeneracy is ubiquitous in biology, from the workings inside a single cell to distributed brain networks. Natural selection favors systems with degeneracy because they are high in complexity and robust to damage. In emotions research, degeneracy means that instances of an emotion, for example, fear, are created by multiple spatiotemporal patterns in varying population of neurons. Therefore, it is unlikely that all instances of an emotion category share a set of core features, for example, a single facial expression, autonomic pattern, or set of neurons. This observation is an example of population thinking pioneered in Darwin's On the Origin of Species. By observing the natural world, Darwin realized that the biological categories, such as species, are conceptual categories. That is, highly variable instances grouped together by a goal rather than similar features or a single shared underlying cause. Barrett hypothesizes that following Darwin's insight, he believes that fear, or any other emotion, is a category that is populated with highly variable instances. The summary representation of any emotion category is an abstraction that need not exist in nature. The fact that human brains effortlessly and automatically construct such representations helps to explain why scientists continue to believe in the classical view and even propose it as an innovation, even as the evidence continues to call it into doubt. What is a brain for? When we ask a question like that, we have to explore the brain's function in detail. A brain did not evolve for rationality, happiness, or accurate perception. All brains accomplish the same core task to efficiently ensure resources for physiological systems within an animal's body, that is, its internal milieu, so that animal can grow, survive, and reproduce. This balancing act is called allostasis. Allostasis is not a condition of the body, but a process for how the brain regulates the body according to the costs and benefits. Efficiency requires the ability to anticipate body's needs and satisfy them before they arise. An animal thrives when it has sufficient resources to explore the world and to consolidate the details of experience within the brain's synaptic connections, making those experiences available to guide the later decisions about future expenditure and deposit. Whatever, whatever else your brain is doing, thinking, feeling, perceiving, emoting, it is also regulating your autonomic nervous system, your immune system, and your endocrine system, as resources are spent in seeking and securing more resources. All animal brains operate in the same manner. This regulation helps explain why, in mammals, the regions that are responsible for implementing allostasis, regions like the amygdala, ventral striatum, insula, orbitofrontal cortex, anterior cingulate cortex, medial prefrontal cortex, collectively called visceromotor regions, are usually assumed to contain the circuits for emotions. In fact, many of these visceromotor regions are some of the most highly connected regions of the brain, and they exchange information with midbrain, brainstem, and spinal cord nuclei that coordinate autonomic, immune, and endocrine systems with one another, as well as with the systems that control skeletal motor movements and that process sensory inputs. Therefore, these regions are clearly multipurpose when it comes to constructing the mental events that we group into mental categories. Now, next we're going to discuss how does a brain perform allostasis. For a brain to effectively regulate its body in the world, it runs an internal model of that body in the world. In psychology, we refer to this modeling as embodied simulation. An internal model is metabolic investment implemented by intrinsic activity that in humans occupy about 20% of the total energy consumed. Given these considerations, modeling the world accurately in some detached, disembodied manner would be metabolically reckless. Instead, the brain models the world from the perspective of its body's physiological needs. As a consequence, a brain's internal model includes not only the relevant statistical regularities in the extrapersonal world, but also the statistical regularities of the internal milieu. Collectively, the representations and utilization of these internal sensations is called interoception. Recent research suggests that interoception is at the core of brain's internal model and arises from the process of allostasis. Interoceptive sensations are usually experienced as low level or low dimensional feelings of affect. As such, the properties of affect, that is, valence and arousal, are basic features of consciousness that, importantly, are not unique to instances of emotion. All animals run an internal model of the world for the purpose of allostasis. Even single cell organisms that lack a brain learn, remember, make predictions, and forage in service of allostasis. The content of any internal model is species specific, however, including only the parts of the animal's physical surroundings that its brain has judged relevant for growth, survival, and reproduction. Everything else is just an extravagance that puts energy regulation at risk. As an animal's integrated physiological state changes constantly throughout the day, its immediate past determines the aspects of the sensory world that concerns the animal in the present, which in turn influences what its niche will contain in the immediate future. This observation prompts an important insight. Neurons do not lie dormant until stimulated by the outside world, denoted as stimulus leading to response. Ample evidence shows that ongoing brain activity influences how brain processes incoming sensory information, and that neurons fire intrinsically within large networks without any need for external stimuli. The implications of these insights are profound. Namely, it is very unlikely that perception, cognition, and emotions are localized in dedicated brain systems, with perception triggering emotions that battle with cognition to control behavior. This means classical accounts of emotion, which rely on this stimulus leading to response narrative, are highly doubtful. Now, next section, we're going to discuss the nature of internal model. An animal's internal model is predictive, not reactive. An increasingly popular hypothesis is that brain simulations function as Bayesian filters for incoming sensory input, driving action, constructing perception, and other psychological phenomena, including emotions. Simulations are thought to function as prediction signals, also known as top down or feedback signals, or more recently as forward models, that continuously anticipate events in the sensory environment. This hypothesis is variously called predictive coding, active inference, or belief propagation. Without an internal model, the brain cannot transform flashes of light into sights, chemicals into smells, and the variable air pressure into music. You will be experientially blind. Thus, simulations are a vital ingredient to guide action and construct perceptions in the present. They're embodied, whole brain representations that anticipate incoming sensory events, both inside the body and out, as well as the best action to deal with the impending sensory events. Their consequences for allostasis is made available in consciousness as affect. Using the past experience as a guide, the brain prepares multiple competing simulations that answer the question, what is this new sensory input most similar to? Similarity is computed with reference to the current sensory array and the associated energy costs and potential rewards for the body. That is, simulation is a partially completed pattern that can classify, that is, categorize sensory signals to guide actions in the service of allostasis. Each simulation has an associated action plan. Using Bayesian logic, our brain uses pattern completion to decide among simulations and implements one of them based on predicted maintenance of physiological efficiency across multiple body systems. From this predictive, unanticipated information from the world, from this perspective, unanticipated information from the world, that is, prediction error, functions as a feedback for embodied simulation, also known as bottom up or feed forward signals. Error signals track the difference between predicted sensations and those that are coming from the sensory world, including body's internal milieu. Once these errors are minimized, simulations also serve as inferences about the causes of sensory events and plans for how to move the body or not to deal with them by modulating ongoing motor and visceromotor actions to deal with upcoming sensory events. A brain infers their likely causes. Now, in predictive coding, as we'll see, sensory predictions arise from motor predictions. Simulations arise as a function of visceromotor predictions to control our autonomic nervous system, our neuroendocrine system and immune system, and the voluntary motor predictions, which together anticipate and prepare for the actions that will be required in a moment from now. These observations reinforce the idea that stimulus leading to response model of the mind is incorrect. For a given event, perception follows and is dependent on action, not the other way around. Therefore, all classical theories of emotions are called into question, even those that explain emotion as iterative stimulus leading to response sequences. Next, we're going to discuss the computational architecture of the brain. Computational architecture of the brain is a conceptual system plus pattern generators. The mechanistic details of predictive coding provide yet another deep insight. A brain implements its internal model with concepts that categorize the sensation to give them meaning. The predictions are concepts. The completed predictions are categorizations that maintain the physiological regulation, guide action, and construct perception. The meaning of a sensory event includes visceromotor and motor action plans to deal with the event. The meaning does not trigger the action, but results from it. This makes classical appraisal theories highly doubtful because they assume that a response derives from a stimulus that is evaluated for its meaning. Traditionally, a category is a population of events or objects that are treated as similar because they all serve a particular goal in some context. A concept is a population of representations that corresponds to those events or objects. Barrett hypothesizes that in assembling populations of predictions, each one having some probability of being the best fit to the current circumstances, the brain is constructing concepts. In the language of the brain, a concept is a group of distributed patterns of activity across some population of neurons. Incoming sensory evidence as prediction error helps to select from or modify this distribution of predictions because certain simulations will better fit the sensory array, with the end result that incoming sensory events are categorized as similar to some set of past experiences. That is, in effect, is the original formulation of conceptual act theory of emotions. Brain constructs meaning by correctly anticipating, that is, predicting and adjusting to the incoming sensations. Sensations are categorized so that they're actionable in a situated way and therefore meaningful based on past experience. When a past experience of emotion, that is happiness, for example, are used to categorize the predicted sensory arrays and guide action, then one experiences and perceives that emotion, that is happiness. In other words, an instance of emotion is constructed the same way that all other perceptions are constructed, using the same well validated neuroanatomical principles for information flow within the brain. The first key observation is that the predicted prediction signals are carried via feedback connections that originate in cortical regions with the least well developed laminar structure, referred to as agranular. Agranular regions are cytoarchitecturally arranged to send but not receive prediction signals within the cerebral cortex. Another name for agranular cortices is limbic. Limbic cortices, such as the anterior cingulate cortex and the ventral portion of the interior insula, allostatically control physiology by relaying descending prediction signal to the internal milieu via a system of subcortical regions, including the nucleus, that is, the central nucleus of amygdala, ventral and dorsal striatum, and the central pattern generators across hypothalamus, parabrachial nucleus, periaqueductal gray, and the solitary nucleus. These visceromotor regions of the brain that are responsible for implementing allostasis and are usually assigned an emotional function are driving the perception signals. That is, the concept that constitute the brain's internal model in conjunction with the hippocampus. A concept is not only the descending prediction signals that control the viscera. It also includes the efferent copies of those signals that cascade to primary motor cortex as skeletal motor prediction signals, as well as all primary sensory cortices as sensory prediction signals. Because motor cortex has a laminar organization that is less well developed than primary visual, auditory, and sensory motor and interoceptive sensory signals or regions. Barrett hypothesizes that motor cortex sends the efferent copies to those sensory regions as sensory predictions. Predictions literally change the firing of primary sensory and motor neurons, even though the incoming sensory information or input has not yet arrived. Accordingly, all action and perception are created with concepts. All concepts contribute to allostasis and represent the changes in affect, not just those that construct the events that feel effectively intense or are created with emotion concepts. To consider this, how this works, try this thought experiment. In the past, you have experienced diverse instances of happiness, maybe lying outdoors on a sunny day, finishing a strenuous workout, hugging a close friend, eating a piece of delectable chocolate, or winning a competition. Each instance is different from every other. And when the brain creates a concept of happiness to categorize and make sense of the upcoming sensory events, it constructs a population of simulation as potential actions and perception, according to the rules of Bayes' theorem, whose priors reflect their similarity to the current situation. And this is done before the evidence is taken into account. The similarity need not to be perceptual. It can be goal-based. So the brain constructs an online concept of happiness, not in absolute terms, but with reference to a particular goal in the situation. For example, to be with friends, to enjoy a meal, or to accomplish a task, all in the service of allostasis. This implies that happiness has a specific meaning, but its specific meaning changes from one instance to the next as the prediction signals cascade across the synapses of a brain. Incoming sensory signals arrive to the brain simultaneously, allow for the computations of the prediction error that are encoded to update the internal model. Viscerosensory prediction errors arise from the physiological changes within the internal milieu and ascend via the vagal and small diameter afferents in the dorsal horn of the spinal cord through the nucleus of solitary tract, parabrachial nucleus, and periaqueductal gray, and finally to the ventral posterior thalamus before arriving in the granular layer 4 of the primary interoceptor insular cortex. Notice that in the context of this framework, perception, that is, the meaning of sensory input, is constructed with reference to allostasis, and the sensory prediction errors are treated at a very basic level as information that guides a predicted visceromotor and motor action plan. Prediction errors also arise within the amygdala, basal ganglia, and cerebellum, and are forwarded to the cortex to correct the internal model. Information from amygdala to cortex is not emotional per se, but signals uncertainty about the predicted sensory input and helps to adjust allostasis via the central nucleus as a result. The arousal signals that are associated with the increase in amygdala activity can be considered as a learning signals. Similarly, prediction errors from the ventral striatum to the cortex convey information about sensory inputs that impact allostasis more than expected. The cerebellum models the prediction errors from the periphery and relay them to the cortex to modify motor predictions. That is, it predicts the sensory consequences of a motor command much faster than actual sensory prediction errors can manage, and helps the cortex to reduce the sensory consequences caused by one's own movement. A brain implements an internal model of the world with concepts because it is metabolically efficient to do so. Even before birth, a brain begins to build its internal model by processing prediction error from the body and the world. Prediction errors, that is, unanticipated sensory input, cascade in a feed forward cortical sweep originating in the upper layer of the cortices with more developed laminar organization and terminating in the deep layers of cortices with less well developed lamination. As the information flows from sensory regions to the limbic and other heteromodal regions in the frontal cortex, it is compressed and reduced in dimensionality. This dimension reduction allows the brain to represent a lot of information with a smaller population of neurons, reducing redundancy and increasing efficiency. Because smaller populations of neurons are summarizing statistical regularities in the spiking patterns in large populations within the sensory and motor regions. Additional efficiency is achieved because conceptually similar representations reuse neural populations during simulation. As a result, different predictions are separable but are not spatially separate. Therefore, the hypothesis is that all new learning, that is, processing of prediction errors, is concept learning because the brain is condensing the redundant firing pattern into more efficient and cost effective multimodal summaries. This information is available for later use by limbic cortices as they generatively initiate prediction signals. Constructed as low dimensional multimodal summaries, these summaries, consolidated from prior encoding of prediction error, become more detailed in particular as they propagate out to more architecturally granular sensory and motor regions to complete embodied concept generations. The next step, we discussed taking a network perspective. Barrett claims that in 2006, she proposed that several of brain's intrinsic network would come to be called default mode salience and frontoparietal control networks are domain general or multi-use networks that are involved in constructing emotional episodes. Barrett claims that default mode network is necessary for brain's internal model. Barrett further hypothesizes that the default mode network hosts part of their patterns, but simulations are more than just multimodal sensory motor summaries. They are fully embodied brain states. They emerge as default mode summaries, cascade out to the primary sensory and motor regions to become detailed and particularized. Barrett further hypothesizes that the salience network tunes the internal model by predicting which prediction errors to pay attention to. That is, those errors that are likely to be allostatically relevant and therefore worth the cost of encoding and consolidation, called the precision signals. Barrett hypothesizes that precision signals optimize the sampling of sensory periphery for allostasis, and they are sent to every sensory system in the brain. They directly alter the gain on neurons that compute prediction errors from the incoming sensory input. That is, they apply attention to signal the degree of confidence in the predictions, that is, in the priors. Confidence in the reliability or the quality of incoming sensory signals and or predictive relevance for allostasis. Unexpected sensory inputs that are anticipated to have resource implications will be treated as signal and learned to better predict energy needs in the future, with all our other predictions error treated as noise and safely ignored. Limbic regions within the salience network may also indirectly signal the precision of incoming sensory input via their modulation of the reticular nucleus that encircles the thalamus and controls the sensory input that reach the cortex via thermocortical pathways. Barrett believes that the cortical limbic regions within the salience network are at the core of brain's ability to adjust its internal model to the conditions of sensory periphery, again in the service of allostasis. Barrett further hypothesizes that neurons with the frontoparietal control network sculpt and maintain simulations for longer than several hundred milliseconds it takes to process imminent prediction errors, and they may also help to suppress or inhibit simulations whose priors are very low. Emotion perceptions, according to Barrett, are event perceptions, not object perceptions. Now, with this background in brain structure and the cytoarchitecture of the brain, now we finally come to the theory of constructed emotion. A brain, as we know, can be thought of as running an internal model that controls central pattern generation in the service of allostasis. An internal model runs on past experiences, implemented as concepts. A concept is a collection of embodied, whole brain representations that predict what is about to happen in the sensory environment and what the best action is to deal with the impending events and their consequences for allostasis. And that is made available to consciousness as affect. Unpredicted information, that is a prediction error, is encoded and consolidated whenever it is predicted to result in a physiological change in state of perceiver. Once the prediction error is minimized, a prediction becomes a perception or an experience. In doing so, the prediction explains the cause of sensory event and directs action. That is, it categorizes the sensory event. In this way, brain uses the past experience to construct a categorization that best fits the situation to guide action. The brain continually constructs concepts and creates categories to identify what sensory inputs are, infers a causal explanation for what caused them, and drives action plan for what to do about them. When an internal model creates an emotion concept, eventual categorization results in an instance of emotion. Constructionism, as a scientific paradigm, makes different assumptions than the classical paradigm, asks different questions, and requires different methods and analytic procedures than those of classical view. As a consequence, constructionism is often profoundly misunderstood. With this observation in mind, Barrett gives a list of claims that she's not making to make to avoid further confusion. Barrett says that she is not saying that emotions are illusions. She is saying that emotions are categories that don't have distinct, dedicated neural essences. Emotion categories are as real as any other conceptual categories that require a human perceiver for existence, such as money. Next, Baird says that she is not saying that all neurons can do everything, also known as acupotentiality. She is suggesting that a given neuron does more than one thing and has more than one receptive field, and there are no emotion specific neurons. Next, she is not claiming that networks are Lego blocks with a static configuration and an essential function. She is suggesting that when it comes to understanding the physical basis of psychological categories, it is necessary to focus on ensembles of neurons rather than individual neurons. A neuron does not function on its own, and many neurons are part of more than one network. Moreover, neurons function via degeneracy, meaning that given a network has a repertoire of functional configuration that is constrained by its anatomical structure. Next, Barrett is not claiming that subcortical regions are irrelevant to emotions. She hypothesizes that an instance of emotion is a brain state that makes the sensory array meaningful, and in so doing, engages the pattern generators for whatever actions are functional in the context, given a person's current state. Next, Barrett is not saying that the default mode and salience network implement allostasis and therefore should not be mapped to other psychological categories. She is claiming that these and other domain general networks can be mapped to many psychological categories at the same time. Further, she is not saying that concepts are stored in the default mode network. She is saying the default mode network represents efficient multimodal summaries from which a cascade of predictions issue through the entire cortical sheet, terminating in the primary sensory and motor regions. The whole cascade is an instance of a concept. Next, Barrett is not saying that emotions are deliberate, nor denying that automaticity exists. She is saying that in humans, actual executive control, that is, for example, via the frontoparietal control networks in primates, and the experience of feeling in control are not synonymous. All animal brains create concepts to categorize sensory inputs and guide action in an obligatory automatic way outside of awareness. Automaticity and the control are different brain modes, not two battling brain systems. Next, Baird is not saying that non human animals are emotionless. She is saying that emotions are perceiver dependent. So, questions about the nature of emotions must include a perceiver. A question like, is the fly fearful? Is not a scientific question. But does a human perceive fear in the fly? Or does the fly feel fear? Can be answered scientifically. And the answers are yes and no. She is not claiming that fly feels nothing. It may feel affect. Now, next we discuss this implications of this theory of constructed emotions. Barrett reports that scientific revolutions are difficult. At the beginning, new paradigms raise more questions than they answer. They may explain existing anomalies or redefine lingering questions out of existence, but they also introduce a new set of questions that can be answered only with new experimental and computational techniques. This is a feature, not a bug, because it fosters scientific discovery. As new paradigm barely gets started before it is criticized for not providing all the answers, but the progress in science is often not answering the old questions, but by asking better ones. The value of the new approach is not never based on answering the questions of the old approach. Such is the case with the theory of constructed emotions. Evidence from the various domains of research is consistent with the proposed hypotheses, even as it casts aside some of the old unanswered questions of the classical view. Ironically, this perhaps the strongest evidence, according to Barrett, to date for the theory comes from the studies that use pattern classifications to distinguish categories of emotions. Several recent articles taking this approach have reported success in differentiating one emotion category from another, a finding that is routinely construed as providing the long awaited support for the classical view. However, the patterns that distinguish among categories in one study do not replicate in the other studies. The same is true for the studies that successfully created different patterns of autonomic physiology, despite using the same stimuli and experimental methods and sampling from the same population. Generally speaking, pattern classification results in the Science of emotion as routinely misinterpreted. A pattern that diagnoses sadness is not the brain state for sadness, but merely a statistical summary of a highly variable set of instances. To assume otherwise is an essentialist error that makes a statistical summary for the norm. Indeed, the voxels that make up a pattern for a category need not observe in every or even any single instance of that category. Scientists carefully map the circuitry for behaviors or mere movements in some cases in non human animals, but some mistakenly believe that they are mapping the circuitry for emotions. An example is observing freezing behavior in a rat, for example, in response to an electric shock, and calling it fear. Rats don't freeze only in situations that we perceive as threatening, that is, one behavior maps to many categories, and rats exhibit a variety of behaviors in threatening situations, that is, many behaviors map to one category. This error, assuming that an action is equivalent to an emotion, which Barrett calls the mental inference fallacy, has wreaked havoc with the scientific accumulation of knowledge about emotion. Motor movements do not provide a direct indication of an internal state, but be it in the rodent, a monkey, or a human. When viewed in this slide, it is an error to claim that studies of human brain using functional MRI yield different results than the studies of non-human animal brains with lesions or optogenetics. In reality, all are making the physical measurements and mapping emotion concepts to them, and no set of findings is described appropriately by classical emotion concepts. For example, in an attempt to deal with all the variation within the category fear, scientists create finer grained typologies in an attempt to bring nature under control and make it easier to identify their essences. But this does not avoid the problem of the mental state fallacy. Furthermore, it makes no sense to elevate categories for anger, sadness, fear, disgust, and happiness to a common ethological framework for comparing humans with other animals, when there is ample evidence from linguistic, anthropology, and psychology that these categories do not offer a robust, universal framework for comparing humans of different cultures. Finally, we discuss the conclusions and future directions. Scientists must abandon essentialism and study emotions in all their variety. We must not merely focus on the few stereotypes that have been stipulated based on the very selective readings of Darwin. We must assume variability to be the norm, rather than a nuisance to be explained after the fact. It will never be possible to measure an emotion by merely measuring the facial movement, muscle movements, changes in autonomic nervous system signals, or neural firing within the periaqueductal gray or the amygdala. To understand the nature of emotion, we must also model the brain system that are necessary for making meaning of physical changes in the body and in the world. This article is a mere sketch of a much larger scientific landscape. The theory of constructed emotion proposes that emotion should be modeled holistically as a whole brain body phenomena in the context. Barrett's key hypothesis is that the dynamics of default mode, salience, and frontoparietal control networks form the computational core of the brain's dynamic internal working model of the body in the world, entertaining sensory and motor systems to create multisensory representations of the world at various timescales from the perspective of the someone who has a body, all in the service of allostasis. In other words, allostasis, that is predictively regulating the internal milieu, and interoception, that is representing the internal milieu, are at the anatomical and functional core of the nervous system. These insights offer a range of new hypotheses. For example, that appraisal, reappraisal, and other regulation processes are accomplished with predictions that categorize sensory inputs and control actions with concepts. Emotions are constructions of the world, not reactions to it. This insight is a game changer for the science of emotions, according to Barrett. It dissolves many of the debates that remain mired in philosophical confusion and allows us to better understand the value of non human animal models without resorting to the perils of essentialism and anthropomorphism. It provides a common framework for understanding mental, physical, and neurodegenerative disorders, and also collapses the artificial boundaries between cognitive, affective, and social neuroscience. Ultimately, the theory of constructed emotion equips scientists with new conceptual tools to solve the age old mysteries of how a human nervous system creates a human mind. With these insights, we come to an end of this article on Theory of Constructed Emotions by Lisa Feldman Barrett. I hope this was helpful and you enjoyed this episode as much as I did. Look forward to seeing you again as we explore further scientific concepts and the constructed emotions and other theories of affective neuroscience.